Today on How It's Made. Headphones. Diving regulators. And reflector light bulbs. In the early part of the 20th century, headphones were used mainly by telephone operators and radio technicians. But in the 1930s, they were redesigned and marketed to the public, so music lovers everywhere plugged in and turned on to the concept. Everyone is a music critic, but headphones allow people to crank up the volume without negative feedback from neighbors. To make high-end headphones, an injection molding machine first makes plastic back covers. The mesh area will allow sound waves to pass through instead of reflecting back into the headphone. Down the line, equipment stamps trademark and other information onto two more casing components, a decorative metal disc and a plastic housing. The next machine winds copper wire that's as thin as human hair around a cylinder hundreds of times. The winding is computer controlled to produce a critical component, the headphone's voice coil. When magnetized by an incoming signal, the voice coil vibrates a diaphragm, causing it to emit sound. That diaphragm now takes shape as a press applies heat and pressure to a plastic membrane. These tools mold the plastic to the desired shape. The press molds the plastic thicker in the center and thinner around the outer zone for a wide and flat audio frequency range. A technician punches out the molded shape. She applies a bead of glue to the diaphragm, then positions the copper voice coil in an assembly device. She aligns the glued section of the diaphragm with the coil. Ultraviolet light activates the glue to seal the coil to the diaphragm. The plastic housings each contain a magnet. The next technician installs the diaphragm and voice coil assembly on that housing. This takes skill because the coil must be positioned precisely for the best sound quality. And this headphone speaker is now ready for an audio check. A technician tests the audio frequency range, distortion, and other factors. Here a technician joins the ends of curved wires in a plastic clip. These wires serve a dual function. They hold the headphones snugly over the ears and deliver audio signals from the left side of the headphones to the right. The next technician installs a connector for the headphone's audio cable and a plastic strain relief. An adjustable band will allow the headphones to fit on heads of all shapes and sizes. The operator presses the parts together with a hydraulic tool. Moving down the line, a technician now joins the two halves of the speaker housing. She forces the two parts together with the pneumatic tool and finishes it off with a decorative metal ring. She inserts the speaker mechanism in the center of the housing, then places plastic brackets over it for protection. She then secures the entire assembly to the housing. Next, she solders two wires to each headphone speaker. A plastic ring and cover protect it while still allowing the wires to protrude. She attaches the end of the headband to the speakers. then solders the wires from the speaker to those protruding from the headband. She presses a plastic grill into place over each speaker, very carefully to prevent scratching. These headphones are now wired and ready for audio. And whether it's rock or classical, the choice of music will be silent to all but one individual. The diving regulator is a lifeline when you're underwater. Invented in 1937, this device converts compressed air from diving tanks into a breathable form and delivers it to the diver via a mouthpiece. And that means once you've taken the plunge, you can breathe easy. The two main parts of a diving regulator are called stages. Computerized tools transform a piece of brass into the first stage housing. They carve a cavity and holes for attaching hoses and other components. A blade cuts the part to size. Then a drill creates a space for the pressure reduction valve. This end also gets holes for more attachments. Another tool sculpts the side to reduce the weight of the part. Sliced in two, this is how the first stage housing looks inside. After it's been chrome-plated, they insert plugs for the holes that will later be used for attaching gauges, hoses, and other parts. The fitting that connects the regulator to the scuba tank goes into a holding device, while the technician assembles a special valve for keeping salt water out. He fits a piston onto the end of a spring, and then slips the assembly through a hole to confirm it's the right size. He installs a filter on the other end of the spring. Now he inserts the valve in the fitting. He secures it with this rubber ring, pressing it into a groove in the fitting. The valve appears to be firmly entrenched. He presses it to confirm it operates correctly. And he pumps water into a bunch of these fittings to confirm the valves inside are indeed watertight. He attaches a rubber cover and a chrome-plated yoke to the fitting. Then installs this assembly in the housing, using a long-handled socket wrench to get the right torque. This yoke swivels to give the diver some flexibility in attaching it to the diving tank. He now assembles a crucial component, the high-pressure reduction valve. Installed inside the first stage housing, it converts high pressure to medium pressure. He caps the yoke with a knob, then inserts a pressure-sensing mechanism at one end of the first stage housing. He covers it with a rubber membrane. As the diver inhales, this membrane will trigger the valve to release more air. The diving regulator's first stage is now complete. He just needs to calibrate the pressure reduction valve inside. He hooks it up to compressed air and adjusts the valve so it reduces air pressure to a precise level. He immerses it in water to test for air leaks. There are a few bubbles from plunging it underwater, but nothing that would indicate a problem. They now move on to the diving regulator's second stage, which will convert the medium pressure air from the first stage to a breathable level. The diver's breathing will trigger this diaphragm to open the air valve. He attached a protective cover, and he's ready to install the second stage valve. After he inserts it in the second stage housing, the technician makes an initial adjustment. Then, using a special tool, he precisely calibrates the valve. He removed the diaphragm for the last steps, so he reinstalls it. Then it's over to a guy with an ear for the job. As air is pumped into the second stage, he listens for hisses that would indicate a leak. Satisfied there are none, he hooks the regulator up to a device that simulates breathing and measures the effort required to inhale. If it checks out, they link the two stages with a hose, and this diving regulator is now equipped to handle the pressure. Good lighting is often a matter of reflection, and that's why early on, lamps often came with reflectors. But in 1935, a company figured out how to make light bulbs with built-in reflectors. Sealing the reflectors inside the bulb kept them clean and maintenance-free. As track lights or in recessed fixtures, reflector bulbs can light up a room at the flick of a switch. The creation of these bulbs begins with the bulb shell, known as the glass envelope. It's comprised of numerous raw ingredients and recycled glass. Production is almost entirely automated. An operator activates equipment that weighs the ingredients and releases them into a huge hopper where they're mixed thoroughly. This concoction then flows into a furnace heated to 2,700 degrees Fahrenheit. It takes up to 24 hours for the mix to melt into a taffy-like glass. It flows between rollers that shape it into a ribbon. One roller has little pockets on the surface, which form the ribbon into segments. These devices, called blowheads, inflate the glass segments through holes in the conveyor chain. This stretches the glass into oblong bubbles called blanks. Iron molds encase the warm and pliable glass blanks. The molds spin as the glass hardens into the desired shape. The glass blanks now look like upside-down martini glasses. This is the reflector bulb's glass envelope. It takes just seconds for a glass blank to be transformed inside one of these molds. The envelopes are still linked by a ribbon of glass at the top, so an automated hammer now gently knocks them free. The glass envelopes cool down slowly. This stage, called annealing, toughens the glass to reduce brittleness. They measure the thickness and diameter of one of the envelopes. If it's not up to standards, the entire production run will be crushed and the glass recycled into new ones. But the envelope is good, and so production continues. They lower the envelopes over nozzles that inject hydrofluoric acid. It coats the inner surface of the glass with a frosty finish that will smooth the light emitted by the bulb and widen the beam. The envelopes now head down a chute into a padded channel that cushions their fall. Guides gently position them. Then other devices thrust them into holders which move them down the line. Next, a robot inserts aluminum wire in a heating coil and places a protective metal dome over top. Suction cups pick up the glass envelopes and slide them onto the wire and dome assemblies. A pump pulls air out of the bulb as an electrical current energizes the heating coil to melt the aluminum wire. The aluminum adheres to the walls of the light bulb shell, giving it a reflective finish. The glass envelopes then move on to be stamped with a company trademark and other information. Meanwhile, on another production line, they're preparing the glass mounts for the filament and wire contacts. A cutting wheel slices them to size. The tubes then travel past a flame, which melts the ends just a bit to make the edges smooth. Once they've cooled, grippers deliver the tubes to a more intense flame, which flares them at one end. Coming up next, we'll show you the inner workings of the reflector light bulb. A reflector light bulb can cast one's surroundings in a whole new light, one that's more intense and focused. The source of this light is an electrified filament of wire, and assembling that filament in the bulb is a very delicate task that's performed entirely by machines. Production now focuses on the glass tube that will serve as the mount for the filament and its electrical contacts. Machinery inserts 2 copper wires into each tube. These are the lead wires that will eventually connect the base of the bulb to the filament and deliver the electric current. These long glass tubes will be used to suck air out of the light bulb, preventing oxygen from reaching the filament and destroying it. They protrude from the glass mount, but that's just temporary. They will later be cut shorter. Torches now melt the glass mount, lead wires, and exhaust tube together. Mechanized fingers then pinch the layers together, and the wires are now encased in glass, but protrude from the glass base. Grippers transfer the closed mounts to a carousel. It revolves to allow the mounts to receive a coil made of tungsten metal. This coil is the filament of the reflector light bulb. Mechanized fingers attach the small coil to hooks on the 2 lead wires. The coiled filament is wobbly, so next it gets some support. First, machinery bends the lead wires to move them and the filament out of the way. Then a robot presses the tip of the glass exhaust tube onto a burner. The tip melts, allowing a metal support wire to be embedded into it. Another robot bends the lead wires to position the filament adjacent to the support wire. The next station loops the wire around the filament. This gives the filament the necessary support, and it stops wobbling. This 2-prong device then straightens out the lead wires. The mount is now upright and riding another carousel. Flippers set it straight so a metal disc can be installed on the pinched section of the mount. This disc is reflective. It will bounce light downward to the shiny coating inside the light bulb to create just the right effect. With the disc wrapped around it, the assembly is now positioned on the next turntable. Suction cups deposit the glass envelope on the assembly to encase the filament and reflective disc inside. The holder twirls the bulb as it travels past a row of torches. The flames melt the neck of the glass envelope and it closes around the glass mount. This secures the filament, contacts, and reflective disc inside the bulb. Another set of torches, heated to a much higher temperature, trims the base of the bulb. Molding devices now move in to shape the bottom of the bulb so a metal base can be fitted to it. A gripper then puts that metal base on a track to meet up with the reflector light bulb. By now, the bulb has been flushed of oxygen and filled with argon gas so it will last longer. The metal base finishes it off and will allow the bulb to be screwed into a light fixture. Another flame heats the metal base to cure adhesive that was pre-applied for a strong bond to the bulb. Then, robots cut off protruding wire and form a contact on the base. It has taken just 12 minutes to assemble this reflector light bulb, but it will provide about 2,000 hours of light. If you have any comments about the show, or if you'd like to suggest topics for future shows, drop us a line at sciencechannel.com/howitsmade.